The local supermarkets here have basically been taken over by a big UK chain called Tesco. So all their products are starting to creep into the stores, including these 3 LED spotlights. And I wondered, are these going to be hackable? Well, there's one way to find out. It's interesting to note, before we even look at this, that it says 3.4 watts equals the 50 watt equivalent. Now, it is a lens in the front, and I have to say that most of these lamps that try to be equivalent to 50 watt tend to be quite high power rated, and as a result of that, they burn out quite quickly. This one is at 3.4 watts, hopefully going to last longer. I measured it at 3.5 watts. And when I plug it in, and I shall plug it into an adapter, so into the GU10 adapter, into the bayonet cap holder, and it does put out a much smaller. See the warmth of that colour? It is actually almost too warm. It's a very strangely golden, or maybe it's just because I've been standing at the bench too long that it's got daylight type white, but it does put out a fairly controlled beam. Now, if I bring in another exhibit here, this one is rated the same lumens but 5 watt. It puts out just a splash of light. So the difference between the 5 watt one, which is rated the same intensity, and this one is that the beam angle is different. It's got that shaping optics on it, which is quite interesting. Anyway, let's take it apart. Reverse engineer it. I don't think there'll be any great surprises here. And then we'll see if we can dooby it. So the spudger, usually with these, and I shall zoom down a little bit. Usually with these, if you just stick the spudger down the side here and lever, oh, that was easier than expected. You usually have to lever it all round. Oh, they've just put a dab of silicone on one side by the look of it. I don't see any elsewhere. Okay, I guess that's all it's needed. Yeah, strange. Quite a complex optical system here. Total internal reflection by the look of it. So what do we have? We've got the LED array, we've got a rectifier, we've got the linear current regulator chip. Do we have what we want, which is the 2 resistors, so we can dooby it by chopping one out? We've got 180 ohm and 82 ohm. Can you see that? We've got the resistors in there. Right, tell you what, I'll reverse engineer this and then we can cut those resistors. We can try cutting one of them out and see what we can change the power rating to. One moment, please. And resume. This is a very typical module light with a linear regulator, nothing particularly special, though what is interesting is that whereas in many of the other LED lights they glue the circuit board in this case they've got 2 screws holding it down onto these little fins. Can you see these little fins in here? I'll just zoom in a little tiny bit here. The little sort of ribbed fins around the side. I wonder how well it couples, although having said that, the circuit board is only running at 3.5 watts, so it's not as dramatic as some of the ones that really grill them. On the back of the circuit board, we have the screw holes and a couple of alignment pinholes. We have the square cutout for the capacitor connector, and then we've got the little round cutouts for poking the leads through. And they have a little sort of positioning system, so to keep the wire away from the edge of the metal. One of the leads that comes up from the back is a 30 ohm resistor. It's a fusible resistor. If you look at the circuit board, the LEDs themselves have 4 sections inside them like that. I'm guessing that each has 3 chips, because I reckon these are 12 chip LEDs to make up for the number. To put things into perspective here, in the UK we've got the full wave rectified supply across that capacitor is going to be the best part of 330-ish volt. Well, let's just calculate that. Say 240, which is the most likely voltage we have here, times 1.41 equals 338. So say 340, and if we've got these LEDs, got 1, 2, 3, 4, 5, 6, 7, 8, 8 times the 12 chips, times 3 volts per chip gives 288. So it's on its way to that. There's still a chunk being dropped across this linear regulator here. This is a guess. You know, I could have probed in, I could have applied voltage across these LEDs, but I didn't. Anyway, we have the capacitor, we've got the incoming supply, the bridge rectifier, the smoothing capacitor. We've got a couple of resistors across that. The purpose of those resistors is to discharge that capacitor quite quickly so the light doesn't fade off. And also, to make sure it doesn't ghost glow with capacitive coupling between switch wires. After that, we've got the linear regulator with a 180 ohm resistor, 1800, which means 180 and a 0 decimal multiplier, so it's just 180. And we've got 82RO, which means 82 ohms, because the R is a decimal point here. That is more or less it. If you look at the schematic, I did try modifying one. The easiest modification to make, which makes it the lowest power, is to get a screwdriver down here with this resistor and then just force the resistor off. But it's going to be trickier. I'm going to try and cut that one shortly on the video. Anyway, the chip it's using is the JW19813. There it is, 3-pin linear regulator, just one programming resistor, and then we get the incoming supply, bridge rectifier, capacitor, and that shunt resistor, and then the LEDs. Super, super simple. And that is just implemented with component values like this. I shall zoom down this a little bit more. There's the incoming supply, there's the fusible resistor. The fusible resistor has two functions. It acts as a fuse if things go horribly wrong. It also limits the inrush current so that when you apply the power, if the power is turned on near the peak of the sine wave and this capacitor is fully discharged, there'll be basically, it's like a wee tiny brief short circuit. A very high current will flow through the bridge rectifier and into the capacitor. This resistor reduces that to a sensible level. What would that be? Hold on. So we calculated 340. I equals V over R, which is, yes, that would be, so 340 divided by the 30 ohms, that would be about 11 amps, that peak current. It also means if you've got a lot of amps, it's less likely to trip a breaker with the inrush current. But there's a tiny little electrolytic capacitor, 2.2 megafarad 400 volt death beam capacitor, two 620k resistors. They're also using two to actually divide the voltage across them. But they're in series to give 1.24 megohm. And then there's this string of LEDs, 8 times 12, 963, 288 volts. That's going down to the JW19813 with the two programming resistors. And chopping one of these resistors off will change the power rating of the light. So at the moment it's the equivalent of 56 ohms. So it's either going to change from 56 to 82 or 180. I can show you already, because I've already chopped one of the resistors off, but I shall open this one up. Is this going to have silicon just at one side again? I think I've got the side with the silicon there. Yes, I did. I bat bullseye right on where the silicon was. So now, there's the resistors. Let me just double check. And now we want to remove that one there. How tiny. Let me just work out how I'm going to do this. Can I nibble that? It's not terribly accessible. But as long as you can break the resistor without breaking the one next to it, I think I've broken that enough. Hold on, I'll just chap this off. I think I've broken the carbon film there. We'll find out. I'll plug it in. Right, let's experiment. See what the power of these has changed. If that one's changed. If it's not, I'll just have another go at that resistor. So we'll bring in the anti, since it's better at the lower power loads. The fun button, for those asking, every time you press it, a lawyer explodes somewhere in the world. I have to control myself with that. Otherwise, I'd just press it all the time. So this started off about 3.5 watts. This one that I've modified by leaving the highest value resistor, has gone 1.2 watts. And the intensity, I mean, it's dropped a lot, but it's still useful as a sort of feature light. And because it's running super low power, almost at the same level as the very first LED lamps that last forever, this will probably last forever too. What about this one? Have I managed to do a modification? 2.5 watts I have. So it's dropped from 3.5 to 2.5, still good brightness, but this will reduce the power dissipation of this lamp greatly. That's a good result. Notice that it's spread a bit of a spread here. If I put the lens over the front, then it should, if it goes back in, it will collimate it back into that tight beam again. So that was a good result. good reduction in the power, 2.5 watts and the 1.2. Where's the lens in this one? So if you decide to dooby, to modify your Tesco lights, do remember that they are operating at mains voltage. Take usual precautions. I just feel obliged to say things like that these days, particularly given the behaviour of, well, the direction YouTube's going. But that is it. So the Tesco lamps, can they be doobied? Can they be modified to the point that they they run at lower power and last longer? And the answer is yes, they can. Oh, there's the colour temperature, 2700K. It is super, super golden warm. But that's it. Yes, they can be hacked, which is a good thing.